Hello and welcome to the DVCon U.S. 2021 from Germany. My name is Aman Kumar and I work as a digital verification engineer. Me and my colleague Sebastian Simon have authored the paper titled A Semi-Formal Verification Methodology for Efficient Configuration Coverage of Highly Configurable Digital Designs. In the next 10 minutes, I will try to briefly explain about our topic and the methodology that we have developed. To start with, modern system on chips are becoming more and more complex these days. And it is not wrong to say that they are even comparable to a Swiss Army knife, since they have or they can perform multiple functionalities using the same chip. In order to make these chips perform multiple functionalities, design engineers often use configurations. These configurations are generics in VHDL or parameters in Verilog or System Verilog. This flexibility of using configurations on the digital design side introduces a challenge on the verification side to verify the functional correctness under every possible parameter setting. The vast number of parameters generally don't allow a brute force approach due to the known limitations of state-of-the-art existing methodologies such as formal verification and simulation-based verification. We have developed a semi-formal verification methodology for efficient configuration coverage of highly configurable digital designs. The methodology focuses on reduced tool runtime based on formal and simulation-based methods that allow high configuration coverage. For the methodology flow, we start with creating a V plan or the verification plan where we jot down all the specifications that needs to be verified in the end. After the V plan is created, we move ahead for the regression plan generation, where the main idea is to identify all the configuration dependent deficiencies in the design. Based on the outcomes of this regression plan generation, which is automated, we either go with simulation-based verification or formal verification. After performing both formal and simulation-based methods, we collect the coverage and, more importantly, that were defined in the regression plan generation. If the configuration coverage is fine, we are done. If not, then we go back and redo the steps again. Important for us is the regression plan generation, where we try to identify all the configuration-dependent deficiencies in the design. And this we do using an automated flow, which covers into three parts: the prepare step, the extract step, and the execute step. In the prepare step, we try to identify all the pairwise configurations and perform pairwise verification. Pairwise verification is based on the fact that design bugs are most commonly triggered by one or interaction of less than three parameters. With a study of over 15 years, it was concluded that on an average, 67% of failures are caused by one parameter, 93% or fewer failures are caused by two-way pairs, and 98% or fewer by three-way combinations. In the prepare step, we try to identify these pairwise configurations using an automated tool from Microsoft called as PICT, or the Pairwise Independent Combinatorial Testing Tool. Once we are done with the pairwise template where we identify these pairwise configurations, we move ahead to the extract step, which is divided again into two parts: the top-down approach and the bottom-up approach. In the top-down approach, we divide it into two parts: the constraints and the equivalence classes. Now, the constraints are basically conditions that apply on these parameters. For example, there could be some condition that ROM address width should always be less than or equal to the RAM address width, and these constraints further limit the pairwise set. On the other hand, we have equivalence classes, which basically says that input or output data is grouped into sets of data that expect to behave same using an equivalence relation. And this equivalence relation is very important for us. For example, let's have a look on a parameter P1, which can have values ranging between 6 to 16. And the specification says that the memory access will be direct if the parameter values are between 6 to 14. However, the memory access will be indirect if the parameter values lie between 15 and 16. So clearly, we have two equivalence relation here, one for the direct access between 6 to 14, and the other one with the indirect access between 15 and 16. And this gives us two equivalence classes: class 1, where the values of P1 can be between 6 to 14, and the class 2, where the values of parameter P1 can be between 15 and 16. Now we can use any one value between these two classes to verify the configuration coverage of the digital design. However, we should also look at the suggestions that are being provided by the ISO 26262, which says that we should use boundary values in addition with equivalence classes. And the studies have also proved that most often the bugs often exist at the boundary values. So for our verification, we will take values 6, 14, 15, and 16 of the parameter P1 for verification. Now that we are done with the top-down approach, let's move on to the bottom-up approach, where we basically try to do formal structural checking. In formal structural checking, we try to identify candidates for block-level formal verification. To understand this better, let's assume that we have a SoC top level, which instantiates multiple design blocks, such as block 1, block 2, and block 3. Now, let's consider a parameter P, which is only being used by block 3, and the output of block 3 is the SoC top level output, which essentially means that parameter P2 is not being used by any other block, and the output of block 3 is not affecting the internal logic of any other blocks as well. Therefore, the automated flow that we have created will identify block 3 as suitable for block level formal verification. And then we ignore the parameter P from pairwise regressions. Now, doing formal verification of these blocks will be an extra effort on the verification side, since there might be an existing system Verilog UVM setup that already verifies this block. However, this will significantly reduce the number of regressions in the end, which is our main goal. Now that we are finished with the extract step, we move on to the execute step, which is the last step of our methodology flow, where we generate the optimized pairwise regressions using the PICT tool. And we also generate the system Verilog configuration coverage file, which contains cover groups, cover points, and cross cover points. We also generate VSIF, or the verification session information file, which is specific to our regression management tool, Cadence vManager, where we generate VSIFs for both simulation and formal verification flows. We also applied this developed methodology on our internal microprocessor IP, which is an automotive microcontroller having internal blocks such as ROM interface, program counter, data register files, FSMs, ALUs, and data bus interface. On the parameter side, it has in total 6 parameters, out of which 2 are feature enabling or disabling parameters, so they can have values either 0 or 1, and the others are bus width parameterizations. Now, important ones for us was a parameter address range 1, which can have values ranging between 1 to 32,767. Now, this is a huge number. On the architecture, this processor is based on the Harvard architecture, which means that we have separated control and data path. It has in principle 6 design parameters, as I mentioned before, and is used in the automotive industry. It is also a safety element out of context or a COG design, and ISO 26262 says that for any COG design, we need to verify all the configurations, and if not, we need to give proper argumentation for that. For the microprocessor IP, we will end up having billions of exhaustive regressions, which will take around billions of days for full regression with the existing system Verilog UVM setup. When we look at the methodology implementation results, we started with billions of regressions. And as soon as we added the new techniques that we defined in the methodology flow, we ended up having 3.5 days of regression runtime with 17 configurations that are most relevant for us. We also achieved 100% configuration coverage that was defined in the config.met flow. Now, to conclude this methodology, we started with the brute force approach, and we realized that this is not possible due to problems such as time-space explosion and state-space explosion. And then our main goal was to identify relevant configurations that expose most configuration-dependent deficiencies in the design. We then moved ahead with the optimized pairwise regression technique, where we used constraints, equivalence classes, block-level formal verification. And of course, the core of our methodology remains pairwise verification. As a result, when we applied this methodology on a microprocessor IP, we found 17 optimized configurations with a runtime of 3.5 days. We also achieved 100% coverage or optimized configuration coverage and exposed 9 bugs. As a future work, we need to define the dependency and independency of parameters, as well as define the trade-off between the time and cost for the regression runtime. Our methodology is effective, efficient, fully automated, complies with the ISO 26262 guidelines, and is scalable, meaning can be applied to any other digital design IP. And with that said, we can conclude that we achieved efficient configuration coverage, which was our main goal. Thank you for listening, and I'm open to your questions.